Today we will finish one more topic related to interfaces, and that is that of curvature. So you might have, if you paid attention in our graduate seminar, there has been some talk of curvature in the recent year. There was 2 or 3 presentations of Falk estimated curvatures of fluid-fluid interfaces on pore scale. And that is one of the things that has become possible because of the high-resolution X-ray imaging in 3 dimensions. Thanks to that advancement, more recently we have started to look into quantifications of curvature, and that is obviously related to our good old friend Young-Laplace equation that relates capillary pressure across the interface to the curvature of the interface. More importantly, what we know is that basically we're going to look at the mathematical curvature estimation from having a description of the surface, but what we are really physically looking into is Young-Laplace equation, where if I have 2 fluids that are at 2 different pressures, the difference between those 2 is called capillary pressure. It's something that we are using a lot for characterizing porous media, as well as this displacement through them. Okay. So basically, the interface between 2 immiscible fluids will curve in order to adjust to that capillary pressure difference. And the equation is capillary pressure is sigma, which is interfacial tension. That is something that depends on fluid-fluid-solid combination. So it's a system of 2 fluids and a solid that will have a related interfacial tension, and then times what is formally twice the mean of the curvature for that surface. And by mean of, we are looking at 2 radii of curving. Can I get a piece of paper? Just a single piece of, I might have one. I have one. Okay. So when I have a surface, this curvature, this is obviously not a curved surface. Okay. So if I was looking at the radius of curviness of this, its radius is infinity. Therefore, 1 over infinity is 0. So this is curvature 0 in any direction you'd like to look. If I curve this surface this way, okay, then obviously in this direction I could fit a sphere here of certain radius. That's one curvature. Okay. And then in this direction, this one here, orthogonal to this one, I actually have also infinity, 1 over infinity, because basically I'm not curved when I look in this direction. I'm obviously not curved, right? I can find a line. So one of these radii is infinity, and the other one is whatever sphere radius I can put in here. So mean, so if I take 1 over R1 is the curvature, plus another one, so here the other one would be infinity, right? And one of them would be. So this is how I get this is formally twice the mean of the curvature, and I'm calling these kappa 1 and kappa 2. In this case, of course, I could slice this orthogonally. Okay? But basically, these 2 orthogonal directions, okay, in this direction I'm getting the minimum, and in this direction I'm getting the maximum curvature. However I slice this system otherwise, I'm going to get some 2 different curvatures that are somewhere in between those 2. So I have 2 extremes, okay? Kappa 1 and kappa 2. Interesting result, and it's a result from differential geometry, is that no matter how you slice this in 2 orthogonal directions, at every point the mean is the same. Think about that both mathematically and physically. So physically, actually, this mean curvature is a physical property. Okay? My interface will curve so that at equilibrium, this mean curvature is constant. Every point of the interface, however complex that interface might be in 3D. Okay? And mathematically, however I slice it and dice it, I'm going to get the same thing. This is a pretty robust result, both from physical and mathematical point of view. So this principal radii of curvature. Now things can get really interesting in 3rd dimension. So before I head out. So one convenient way, and those of you who know a little bit about my research know that I have developed some level set methods for displacement of interfaces. If you have a so-called level set function, just like we've been doing these iso surfaces, right? They're level set at certain level. So if you have an implicitly defined interface, here is one. I'm defining this interface to be a contour wherever this function that I call phi is 0. It could be any other. It could be 2, it could be 7, it could be whatever it is that I want. So let's say that it's a 0. Well, then inside this will be where my phi is negative. Outside will be where phi is positive. Okay? 0 is the actual interface. In this case, a contour in 2D. In 3D, it would be an isosurface that you're going to have fun printing. Okay? And I have a normal. Normal is normal. It's orthogonal to the interface. So it's actually a gradient of the function. Gradient is orthogonal to the interface, to anything that is constant. Okay? Gradient physically is always pointing in the direction where the function is taking the most change. Yes? So gradient is the direction of the largest change. And where function is constant is the least change, relative change, right? If I'm constant as I'm moving around this interface, that's where I'm least changing. Okay? So the two directions are orthogonal, physically. And think about what that means in terms of pressures and so forth if you think about fields in general. Okay, now mean curvature is really divergence. Those of you who have taken transport love that operator, don't you? Divergence of the normal is actually curvature mathematically. Point of all of this is that this is a standard operator in general in calculus, okay, multivariate calculus. Normal gradient is a standard operator in multivariate calculus. Therefore, I have a formula for this. Okay? And that formula, as clunky as it is, here it is. Okay? It's a whole bunch of first order and second order derivatives of this function phi. That's all you need to know. And you can look up the formula, you can calculate it yourself. Okay? And if you have a stencil, a standard discretization, finite different discretization will give you these fields, and you will be able to calculate. This is the mean curvature. So this is the mean of these two orthogonal curvatures. Now, what's interesting again, and here I'm actually plotting. This is from a simulation. It's actually a little hard to see, but this is, I split the surface of non-wetting fluid into gray part, which is in contact with solid, and into colored part, which is in contact with the wetting fluid. So when I split the two, these colors show a range of kappa 1 and a range of kappa 2. The whole point is that this is a constant mean curvature surface from the simulation. Okay? Pretty good constant. It's a second order differential equation. Got pretty good result to it. Okay? Converges pretty nicely. However, I will have a range of kappa 1s and a range of kappa 2s. Some of them are actually negative, but they average to a constant value across the entire surface. That's this whole point that I'm making in 3 dimensions. If I have in 2 dimensions, okay, in 2 dimensions, I have only one curvature. So if I'm looking at the constant curvature curve in 2D, the only possibility for me is to be part of a circle. The only, one and only. In 3D, okay, I can obviously see a range of curvatures, and this animal is curving in between spheres. Obviously, I have some spheres here. Okay? So it's actually interfacing between spheres. That is a little hard to visualize now. But I'm going to have a constant mean curvature. Now, what it actually comes down to in this case, so let's say that I have at any point, we know that my constant curvature of 0 is this flat plane. Yes? Now if I take a saddle surface that is curved like this, with the radius r in this direction, and orthogonal to it, it's curved like radius minus r, these things have direction in this direction. 1 over r minus minus 1 over r is 0. For any r, I can get a saddle, constant, 0, curvature, interface with that. I have infinitely many possibilities for any constant curvature surface. What it then comes down to fluid passing through a porous medium. Let's say that you're cranking up pressure and you're doing drainage or imbibition experiment in your lab. That fluids will go until it figures out a spot where it can anchor itself to the solid surface at a given contact angle too, and assume this constant mean curvature surface, which is this complicated beast. Okay? And fluid figures it out. If it cannot figure it out, it's just going to pass through. And I drain, revive. So it's an amazing increment in complexity from 2D to 3D. And fluids constantly do that. And we have these complex surfaces, and which is why what's making difficult for us to predict where fluid configurations are. And there's never a single solution to a given curvature. I also depend on the history, where it is that I came from. What was my starting point before I figure out my next step? And we know all of that from our experience with fluids and porous medium. All right, now mathematically, I can classify these curvatures. There's also, the way to classify surfaces is by looking at the multiplication of these two. Again, I have a formula for it. Just disregard this. It's there for you if you need to ever compute it for some reason. And if you need a code for it, let me know. Kappa 1 times kappa 2. Okay. So technically, what I'm going to look at here is also whether curvature is positive or negative, not just what it sums up to. So if I have two of them of opposite sign, I'm going to have a so-called hyperbolic surface. This is just the one that I now described, with it being curved in two different directions with the same radius of curvature. Will give you a curvature 0 or close to 0. If you switch that a little, if you move that a little, you're going to have a so-called hyperbolic surface. If both curvatures are positive, you're going to get an elliptic surface. Parabolic surface has one of the curvatures 0. That's the first example that I've shown. And so-called planar, at least locally planar curvature is 0. This is the one, this is one of the infinitely many possibilities to have a 0 mean curvature. So this is some of the cool stuff. And if you have a level set function, or you have implicitly defined surface with a level set function, that this is your formula. Cool. All right. So I'm not gonna. There's a way to calculate curvatures in image J. It's been a little noisy, and I haven't been happy with that plugin, so I didn't want to exemplify it here, but you can actually find it yourself if you'd like. I'm just going to show some of the recent research on looking at the both curvatures and showing curvatures in the pore space, basically from imaged experiments, and then also showing how we can assess wettability and wettability alteration using curvatures. So there's, Aviso is not there under that name anymore. It is now PGE383, but that is the only software out there in the paid domain that has good algorithm for both curvatures and surfaces, and they're using modified marching cubes algorithm. So this is what was used in this work, and there was a little bit of smoothing to the data so that surface that is obtained is a little smoother, which affects curvature results a lot. Okay? And basically, the way they estimate curvature surfaces, that is, so one way is from the level set functions that I've shown. With segmented data, those might be a little problematic, so you should have a distance field or something that is smooth in itself defining that interface. And if not, one way to do is basically locally to the surface that you have, fit a quadratic form. So in a local coordinate system, you have q of x1, x2, this is so-called quadratic form. Okay? So if you fit this locally, we know how to fit things. Okay? you fit this locally, basically this is equivalent to the X transpose a matrix A times X. Then eigenvalues of this matrix are essentially your principal curvatures. So that's kind of a cool geometrical result. So what you need to know is some data fitting, as long as you have functional form of what are you fitting to, and enough points around it, you can do that. And once you do that, then you get a quadratic form like this. Then you estimate curvatures by looking at the eigenvalues, and also eigenvectors will give you the directions of these principal directions. Okay? Because all of these principal curvature values also have principal directions. Cool. It's like one of the 700 applications of eigenvalues. Have you ever, in your undergraduate studies, probably somebody on your first or second year of undergrad was really trying to make a point to you how important eigenvalues of a matrix are, and this is one of those cases. Another thing is analysis of ODEs and PCA. And any kind of PCA, and then also in any kind of analysis, main modes of anything will be principal eigenvalues, and then you can, if you have 20 of them, you just take first 5 and run with them if you're filtering anything or cleaning up any data and so forth. So eigenvalues are everywhere, bless you. And they are apparently here in mean curvatures as well. Cool. So this is just how to compute them. If you were going to test on anything, take a known system and test your code. So if you're using somebody else's code, get yourself some spheres. Spheres have constant curvatures. Both principal curvatures are one and only and the same. Okay? And basically test it on a sphere before moving on. Okay? Here, this was actually tested on some capillary tube data, same data that we tested surfaces on. Okay? So this was tested code. So if I had a constant curvature, let's say that I have a sphere packing, all of them are spheres, then I'm going to expect a single value. Right? Except that a single value, I always have a little bit of noise or numerical error. So essentially, what do you expect to get here as a curvature? I'm hinting there's some average or some normal distribution, as long as it's relatively narrow. Okay, for numerical errors and whatnot, you should get a single value. Okay, so something like this. So this was what was obtained by testing on a sphere pack. This is that same precision bead pack that we've been tracking all along for surfaces as well. So plus minus 5% of the true radius of those beads. Cool. Now, if I actually do images, okay, I can look at my connected phases. And the interesting things are basically this connected vetting phase around in a sphere pack is these so-called pendular rings around sphere contacts, which are low resolution. No matter which resolution you have, those are going to be rather low resolution because they're near sphere contacts. Okay? So you're going to have more numerical error. Also, some of them will be bending in different directions, so curvature results could be interesting here. Okay? And this is disconnected non-vetting phase, and you can see coloring by mean curvature. So you can see some negative values showing up to positive values. So essentially, you're going to, even though you technically shouldn't have mean curvature that is negative, because of some numerical issues, you might get some. And you can also see that regardless of imbibition versus drainage, as I'm moving through, I might be disconnecting some of the phase. Let's say that I'm in imbibition and I'm disconnecting the non-vetting phase. That's my residual saturation whirl or whatever it is. The pressure that I disconnect this blob at corresponds to certain curvature. Okay? And if I disconnect and I'm not connected to the pressure inlets and outlets, that's when I'm going to get disconnected at. So my disconnected phase will have, give or take, the curvature that it was disconnected at. So even though I might establish an equilibrium in my connected phase, okay, and a across the main meniscus, I might have certain current curvature / capillary pressure. Disconnected phase will have its own thing going. And you should also see that when you measure things from images. And I can then also track, basically if I'm looking at the history of inhibition and drainage, without going into the details what this was, okay? Basically I will actually see certain times when I disconnected a lot of phase during drainage versus during inhibition, okay? I'm going to see different peaks in my curvature distribution. So that's something to be expected. And then you can also see shift in those. So basically you have oil-water interfacial curvature histograms. You can do water-wet system, which is dashed, and solid, which is oil-wet, and you can actually, even though the beads were the same size, you will see a shift in curvature between oil-wet and water-wet. So it's just another way to monitor the wettability and how different systems compare. So it's another measure along with surfaces, surface areas, and all other connectivity of the blobs. And we have looked at how was the homework. Was it fun? How long did it take?
The longer part was the 8.
Mm-hmm.
Like
Yeah, this is a little, 1 day? Yeah, this is a little larger because it's a sizable, but that's the type of or size of the image that you actually want to analyze if you're doing anything of importance. So again, curvature is another measure. We're not gonna, no homework on curvatures, but if you need to, in your own research, if you need to, it's one of the measures, especially if you're working in enhanced oil recovery and you have good images, it might be something to look into. There is actually, on Digital Rocks portal, there's a really high precision data set by Charlotte Gehring from Stanford University, that if you want to practice measuring curvature, that would be a great set at very high precision than at synchrotron.
So what's, like, would that lead to, what does that plot tell us? Other than you just said it's another parameter.
So here it's a shift in wettability, okay? Because I'm going to get in, based on the wettability, so wettability also entered that formula. It enters, technically I should also have a cosine theta in there, where theta is your angle. So that will take a shift, and it will basically, if you're keeping the same capillary pressure, okay, for the same capillary pressure, because of that cosine theta shift, it's still a constant, or it's assumed constant, it's more complex than that. You're going to see a shift in measured curvatures. Because of that contact angle, the curvatures of fluid-fluid interface, that fluid-fluid pair, can assume on pore scale will be different because of the wettability. Okay. So you can use that as one other angle of inquiry if your interest is in the wettability of surfaces and how it affects displacement. More importantly, how it affects disconnection of the phases. Because we're in petroleum engineering department.
Yeah, okay. That's not really goes
we love residual phase, and what does residual phase do? But even if it's geophysics helping petroleum engineers, you're after that disconnected phase and the residuals that you might have.
Thank you.
But again, this is from you need high resolution images for this. Okay. This is not to say that possibly on the large scale I might have certain curvature to an interface, general interface that is on a larger reservoir scale. Okay? All right. So this is a detail. Whoops, this is undergrad. Jacobi iteration. Okay, we're going to move on to the next topic. And that one is on skeletonization. Did I? I did start. Yes, I did start the recording. Let me double check. So now we're moving on to sort of one final advanced characterization topic for my meeting. And then whatever is left, whatever time is left in the course, we're going to look at some of the simulations. So full simulation, probably 2 or 3 topics on that one. So this is another way to look at images, and specifically homework related to this will be something that is accepted as the most common four-throat network approach, or getting a so-called four-throat network, equivalently grain-grain network from images. So a lot of you should be interested in that type of characterization, or whatever type of research that you need to do. So we're going to start with so-called skeletonization. This is a bit of a historical lesson. This is how I started looking at four-throat networks. Right now, medial axis, or skeleton of the image, is mostly used for visualization. And there are different ways to look at the four-throat networks, but I used it as one way to reduce the complexity and figure out what my four-throat network is. So let's get going. So medial axis, here there's an image of a little ballerina, and what we are thinking of a skeleton is kind of similar to human skeleton, running through the approximate middle of the body. Okay. Now, I could, depending, this is a 2-dimensional world. In 3-dimensional world, depending on what type of space I have, I might actually see some sort of medial surface through it too. So if I'm thinking about the fracture in a porous medium, I'm expecting to see an entire medial surface in between. My name starts with M. This is the solid line, would be a medial axis of the letter N. Now this is all cool, but we need actual algorithms that arrive at this skeleton. Why is it important to do a skeleton? Well, one of you is actually doing so-called fly-through visualization through a medium. So the idea is, hey, can I go through a complex interface? This actually started in colonoscopy, give or take, in medical imaging. That's where you're aiding doctors in walking through a colon. You take an image of a colon, and basically they're looking at polyps and whatever it is that they're looking at when they're doing colonoscopy. So that's one very practical application of colonoscopy. Of fly-through visualization. Imagine we're doing that through a porous medium. Well, a general porous medium, any sample of these samples that are walking around, they're all stacked in the back. You have to start on one side and somehow get to the other side. Okay? Finding a path that really gets you from one side to the other is not necessarily simple, especially if my entire search space is entire pore space. You've spent one day on that homework of yours, okay? Because that 3D image of a biofilm or whatever is a complex creature in 3 dimensions. So getting from one side to the other, having a dedicated path, passing through, searching for it is not easy. So a lot of these algorithms that we're going to mention here, erosion is actually one of them. Erosion is how we get to it. Are basically trying to reduce the complexity of this material, and then I can organize this into a graph. Okay, this red thing is a graph. Graph theory is a very rich field. There's numerous algorithms. They're very speedy. There's any application you can imagine, from scheduling flights to anything else, goes through graphs. Facebook is a graph. Okay, who is connected to whom? If you want to do sociology research, you use graphs. So there's a lot of ready-to-go tools to analyze graphs, and on a graph, it's much an easier task to find this, start one point, get to the other point, the other end. Okay, so just simple task of getting to the other end of the medium. So this is where we might use this medial axis. So basic idea is this reduction of the 3D objects, and I went ahead of myself and I already narrated a bunch of applications for it, but I want to reduce my space or my object to a graph that is easier to search. If I was flying through, then I would identify that path and basically go from toe to head of the ballerina. okay? And I would go through the main path without straying to her skirt, okay? Because I know that my skirt here is dead end and I'm not gonna get to the top of my image. So that is one practical application. Now, this is easier to understand, it's easier to visualize. This skeleton still, you know, when we see a skeleton of a person, we still recognize it's a person for a reason. It resembles, topologically resembles the original image. And we know that the topologically skeleton and the full person are the same thing, which is really helpful to me when I gain some weight. I think to myself, well, topologically, I'm still the same person. I just gained another layer. Okay, so this is how you have to talk to yourself after having two children. And those layers don't go. Erosion is not so. It's easier to dilate than to erode. So okay. So an example applications is visualization, virtual navigation of any sort. Okay, if I was in drilling. We have a big drilling center here. Right? People are navigating through Mother Earth and turning things around, and obviously following a path during drilling, and doing so quickly and in real time. You often have persons sitting in Houston navigating a drill bit in Nigeria, not a small task. So how do you do that with large images and so forth in real time is important. I would also possibly, if I have these reductions of my pore space, I'd like to register the images and try to align them. So there's benefits in trying to do alignment between different objects and any kind of shape recognitions and morphological analysis, which is what you essentially did to an extent for your phone. Okay? And in porous media, we're going to do grain-grain network extraction as well as pore-throat network extraction. Okay. So let's see how do I get candidates for medial axis. The basic idea is so-called that of a grass fire algorithm that we already mentioned. And what it means is like start a slow burning fire at the edges of the object and start burning in. Where these fire fronts meet, okay? If I was in a fracture, obviously, if I'm going from two opposite sides, I'm going to meet in the middle at the medial surface. Okay? So basically, that's going to be my great candidates for this medial surface or medial axis in 3D. So essentially, the requirement is that, so here you can see that a fire starting here and from here would meet here in the middle, but because I have a competing fire here from the sides, this is what I get on the edges, okay? If I'm starting the fire from here, 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 and here, which is my edges of the object. Okay? Mathematically, if I placed an inscribed sphere, the largest inscribed sphere I can at this point, it's going to have minimum of 2 contacts with the grain surface. That's what mathematically these candidates are. Of course, if I do that in 3D, I'm going to have a sphere, and then everything is a little more complex in sphere. So if I was doing the medial axis or candidates in this box, I would actually get this medial surface piece as well as medial axes on the sides. So basically, the centers of all so-called bitangent circles that fit entirely within the objects would be the candidates for the medial axis. Now, once I do this in a general digitized image, I'm going to have my friend noise interfere with life. Okay? So if you have something like this, literally a little nook in your surface, okay? The medial axis is going to try to reach into that nook. This is how it's going to look like. So suddenly, even technically, I want to see this object as a rectangle and I don't care about this small little surface thing. My medial axis will result, instead of having that nice little object there, this is what I'm going to get because of this one surface thing. So small changes in the surface or in general in my object will result in small changes. So these are the results for all of these 3 objects. Okay. If I have any errors or noise in my segmentation, such as this. This is a phone. This is how phones used to look like in some other era. It's hilarious how everybody still recognizes this as a phone. Have you seen a phone like this anytime? The only time I see this phone is in my kids' toys. 3-year-olds still have toys that look like this. Anyway. So you have some images that have issues like this. This is what your medial axis is going to be because of those noises. And any kind of small speckle will cause a medial axis to circle around it. Okay? If you just throw in some salt and pepper noise, this is what you're going to get here. Okay? So noise is always quality segmentation, as I say over and over and over in this class. Quality segmentation is a problem.
This algorithm to work is required for the image to be binary, right?
Yeah. Second thing, so once we actually have these, possibly, let's say that I have a medial surface, but let's say that I'm into my graphs and I want to actually have a graph so I can find a path from one end to the other. Then I would like to reduce this medial surface portion also into a couple of paths going across. Okay? So if I want to do that, I'm going to go and basically, so I found my candidates. These are original my candidates. I'm going to thin them down using erosion algorithm. The only thing that I'm going to check every time I'm going to take candidate by candidate. Let's say voxel here 5. This is my original object I'm going to try to thin down. I'm going to examine 5 and I'm going to say, hey, has Euler characteristic locally changed? If it hasn't, I preserved my topology and I can remove it. If it's going to change, meaning if I disconnect my object, for instance, into 2, my Euler characteristic is going to change, and therefore I'm going to keep that voxel intact and not erode it. So that's basically the algorithm. Go and examine, locally compute these. We're not going to do that, but just so you know, basically I'm going to erode my object while preserving topology so that I don't disconnect pieces and get more connected pieces than I had to begin with.
Could that workflow be done using local maximas?
You could, that the local maxima would still give you just the candidates. Yes. So the same local maxima would be actually your candidates for medial axis or medial surface, and then you still have to thin them down.
There's the canny edge detection algorithm.
Mm-hmm.
Kinds of does something similar to this. You have like a thick edge and kinds of reduce it using the threshold and the local maxima.
Yes, but you want to keep it connected. So the problem with local maxima is that you could have something like this, mm-hmm. right? And then you're going to just keep the maxima, but not what connects them, even though they are locally maxima as well. Okay. So you want to keep it connected so that you don't disconnect your ballerina.
Right.
You don't want to cut her in half. Okay. So that's basically, so your local maxima are, and that's, we're going to get to the watershed algorithm that is basically doing that. And then those are your candidates. The only thing is like you could slightly get a slightly different object depending on the order you're processing these to remove them. Okay, that's the only thing. But they are still locally, it's plus minus a voxel or 2 here and there, so it's not a big deal. Okay, we're going to try this out next time. Mm-hmm.
Good question.